Yes, we're good. Okay, so, guys, roots of a polynomial are the zeros, are the solutions. If we have real roots, they're going to cross the x-axis, correct, everybody? If we have imaginary roots, they won't cross the x-axis. But we still have roots, they're just not real if they don't cross the x-axis. Now, some vocabulary. Rational means can be written as a fraction. So these are all examples of rationals: 1/6, 2/3, 3, and -5. Technically, 3 is a rational. Isn't 3 3/1? So it can be written as a fraction. So today we're going to be learning theorems that have to do with roots of a polynomial. So solutions, zeros of a polynomial. And the first thing we're going to be dealing with is rational roots. So that means fractional roots, correct, everybody? So we all understand when I say rational root what I'm talking about. A root that can be written as a fraction. Okay, sweet. All right, so understand something, guys. We like factoring because if we have a polynomial and we factor it down to linear factors, then it's easily solvable, correct? If it's factorable, it's solvable. Now also, if it's factorable, and you can factor it all the way down, for example, if we have a cubic, why is it degree 3? Because we have 3 x's, correct? If we had a cubic that, for example, factored to be something like this, then we would say, okay, we have linear factors, we would set each of those equal to 0 and solve. If it's factorable, you're going to have rational roots. I'm going to say that again. If it is factorable, then you're going to have rational roots, meaning roots that can be written as a fraction. So if a polynomial is not factorable at a certain point, then that's when we're dealing with irrational roots, such as x is equal to 2/3 of 3, and x is equal to -2/3 of 3. And then also when we have imaginary roots. So these ones, guys, are real roots. They're going to cross the x-axis, correct? Yeah. But they can't be written as a fraction. These ones would be roots that never cross the x-axis. Okay, so that brings me to the rational root theorem. Now, you can't get caught up in the lingo. It's a really actually easy idea, but this kind of makes it seem complicated. So I'm just going to briefly read through it, and then I'll explain it in simpler terms here. So when we have these huge polynomials, let's say it's degree like 10. If we have this huge polynomial of degree 10, and then we have a leading term means highest degree, correct? We have a leading term with a coefficient in front of it. Like let's say the coefficient in front of the leading term is 24. Doesn't 24 have a ton of factors? Factors mean what multiply to be it. And if we have a constant coefficient, that means the constant at the end. Let's say we have, for example, 200. Doesn't that have tons of factors? If we have a polynomial like that, we're still expected to be able to solve it. However, it's going to be really hard to solve it by factoring, correct? Okay, that's what the rational root theorem helps us out with. So, the factors of numbers a sub n, which is just the leading term's coefficient, and a sub naught, which is just the constant. The factors of the leading coefficient and the constant coefficient can help you factor a polynomial as long as the polynomial is set equal to 0. One way to find a root of the polynomial equation is to guess and check. So we kind of do that with factoring a quadratic in a sense. We do what multiplies to be a times c. Are we looking at the coefficient that's in the leading term and the constant? And then adds up to be b. But with the quadratic, we have a method that can kind of help us solve it by factoring. So anyways, one way to find the root of a polynomial equation when the polynomial is set equal to 0 is to guess and check. Now this is not a sufficient way unless there is a way to minimize the number of ways we can guess and check. Because if I gave you, for example, this polynomial and said find the solutions, just looking at it, couldn't it be like anything? Yeah. We would be guessing and checking forever, correct? Yeah. So the rational root theorem just gives us a way to minimize the guesses. So this is the rational root theorem. Here it is. Okay, so let a polynomial of any degree, that's just what this is saying, be a polynomial with integer coefficients. Integer means whole numbers. So if we have whole numbers in front of our variables, then those are integer coefficients. So if we have a polynomial with integer coefficients and the polynomial is set equal to 0, then there are a limited number of possible roots. So it's not everything like we would suspect before this lesson. Integer roots, whole number roots, will be factors of a sub naught. So our integer roots will be factors of this ending term here. Factors mean what multiply to be it. And rational roots, meaning fractional roots, will have reduced form p over q. where P is a factor of A sub naught, and Q is a factor of A sub n. So what we're going to do is we're going to list out factors of P, we're going to list out factors of Q, and then we're going to look at all possible P over Q's. These are going to be the only possible rational roots of the polynomial. So if they're rational, that means can be written as a fraction. Does everybody kind of understand? You probably don't understand the rational root theorem just from reading that. Do you understand the general idea? Okay, so let's go to our first example here. So if we have this, it's just quadratic, but notice how we have 21x squared plus 29x plus 10. We would call our P our constant and our Q is the coefficient in front of the highest degree. Does everybody understand where P and Q come from? That's always going to be what P and Q is. So we're going to list out factors of 10. List out factors of P. 1, 2, 5, and 10. And technically, plus and minus 1. Like we have positive 1 or it could be negative 1. Does that make sense? So we're listing out positive and negative factors of 10. And then Q, we're going to list out factors of Q. So 21. 1, 3, 7, and 21. Those are the factors of Q. So now this, it just tells you the answers. The roots are negative 2/3 and negative 5/7. So how we would have got that was done P over Q. So do you see how 2 over 3 is P over Q? That's one of our solutions. And then negative 5/7, negative 5 over 7 is negative 5/7. That was a solution. So P over Q, we're going to list out all the possibilities and then we're going to test them to see which ones they are. So let's do our first example and then it will make sense, I promise. Here we go. So look up here. Just look with your eyeball. You don't even have to write it down. I would just look and then we'll practice one off your worksheet. So we have this cubic polynomial. Where the first thing we're going to do is say right now, it looks like any number could be, anything could be our solution. But now we've just learned the rational root theorem, so we're going to do a guess and check method, but with with much less guessing and checking. So here we go. This is Q. Does everybody understand that that is not Q? That is P. This is P. This is Q. Is everybody good with that? My leading term is going to be Q, the coefficient, and P is our constant. So I'm going to list out factors of P, you guys. What are some factors of 5? Plus and minus 1, plus and minus 5. Now I'm going to list out factors of Q. Plus and minus 1, plus and minus 2. So the possible rational roots, meaning if we have whole number roots or fractional roots, it's going to be some P divided by Q. So we better do all P's divided by all Q's. So I'm going to start with 1. 1 over 1 is 1, correct? So possibilities are plus and minus 1. 1 over 2, that's a P over Q, so plus or minus a half. And now let's go to 5. 5 over 1 is a possibility, that's a P over Q. And then 5 over 2, correct? So I listed out all possible P's over Q's. So guys, if it's crossing the x-axis and it's a root that can be written as a fraction, it's going to be one of these. So there's 1, 2, 3, 4, 5, 6, 7, 8 possibilities, which is still quite a bit, right? But a lot less than anything. Does everybody understand? Okay, so now think about it. There's a couple different ways we can figure out if these are roots. If we did synthetic division with a root and got a remainder of 0, doesn't that mean it's a root? That's one way of testing it. Also, if we plug in negative 1 into the function and we get 0 out, wouldn't that be a point? Like, for example, let's say we plug in negative 1 and we get 0 out. Isn't that the point negative 1, 0? Wouldn't that be a solution, since that would be where it's crossing the x-axis? I like to test it with that instead of synthetic division, but you can do whatever. So what you're going to do is, yeah, you're just guessing and checking. So let's just start with 1. Here we go. So here we go. Plug in 1 into your function. So you're going to do 2 times 1 cubed minus 1 squared plus 2 times 1 plus 5. You're testing it. Go. Calculate it. Calculate it. The quicker you guys go, the quicker this is. We're going to test negative 1. So I want that table back there. You're going to test negative 1. Okay? So 2 times negative 1. Oh, I don't need. Oh, wait. Robert is asking me? Oh, okay. 90. Yep. So 2 times negative 1 cubed minus negative 1 squared plus 2 times negative 1 plus 5 equals 0. Okay, I'm going to have this table. You guys, how about you guys test positive a half? So you'll be doing 2 times 1 half cubed minus 1/2 squared plus 2 times 1/2 plus 5 equals 0. Do you guys see what you're doing here? We're just testing them. So everybody pick something to test. So when you plug in 1, what'd you get? 1/8, so that wasn't a solution, right? So 1 wasn't a solution, okay? What about -1? Okay, -1, 0, we found a solution. And did you test this one? Okay, so we know that 1/2 isn't a solution. So you plugged in 1/2 and got 6. Okay, so now instead of keeping the testing, guys, think about it. It was cubic, correct? Instead of keep testing, I'm going to just do synthetic division with the root I found. And then won't it become quadratic? And then if the quadratic's factorable, then we have 2 more rational roots. If not, this is our only rational root. So from here, now that I found one, I'm going to use synthetic division using that root. So I go -1. I put in my little thing. Coefficients in front of the variables. 2, -1, 2, and 5. Let's go through this. Okay, let's get down here. 2 times -1 is -2. Stay with me because I might make an error. I'm going fast. We add straight down to -3 times 1 is, add straight down to 5, 5 times -1, add straight down 0. It better be 0 because that was a root. Remainder constant x squared. Let's see if this factors. So we have 2x squared minus 3x plus 5 equals 0. Aren't we looking for what multiplies to be 8 times c? What multiplies to be 10 and adds up to be -3. 5 times 2, but it would be -5 positive 2. Does that multiply to be positive 10? No. No. Are there any other factors? No. So it didn't factor. So we would have to use the quadratic formula, which would give us either imaginary roots or irrational, correct? Yeah. So can we now say that -1 is our only rational root? Yes. And we're done. Does that make sense? Okay. Let's do number 4 together. It's going to take an army. It's going to take an army. We're going to work together. Here we go. So it says find all the rational roots. So what we're going to do, now some of you are thinking, oh, I'm just going to graph it in my graphing calculator and look and see where it crosses the x-axis. We're taking away your calculators for the test. So you'll have to be able to use a, what's it called? Scientific calculator. So if you're thinking, oh, I'm just going to use my calculator, you're in honors. In regular, I'd say, please do. But you're in honors, so you don't get a calculator. So we have to be able to do it. Here we go. So this is my Q, correct? Yeah. This is my P. Sweet. Yeah. The negatives don't matter. Let's list out possible P's. Factors of P. Sorry. 1, 2, and 4. Correct? Q. Plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4. We're listing out factors of 12, plus and minus 6, plus and minus 12. Now we have to do P divided by Q, all possible P divided by Q. 1 over 1 is 1, correct? 1/2. Do you see what I'm doing, everybody? If not, say no. 1/3, okay. 1/4. 1/6 is a possibility, and 1/12. Okay, let's go on to 2. So 2 is a possibility. 2 over 2 is 1. We've already listed that. 2/3, we haven't listed that. So plus and minus 2/3. 2/4 is a half, right? We've already listed it. 2/6 is a third. We've already listed that. 2/12 is a sixth. All right, moving on to 4. Did I miss anything? 4 over 1 is 4. 4 over 2 is 2. We've already listed 2. 4/3. We have not listed that one. And 4/4 is 1. We've listed that. 4/6 is 2/3. We've listed that. 4/12 is 1/3. We've listed that. So these, guys, if this is crossing, if this has a root, if this has roots that are crossing the x-axis and they can be written as a fraction, it's one of these or multiple of these. So what we're going to do is start testing them. It's just tedious. It is. So ready? Let's all take different ones, how about, and work together. Now, yeah, it's tedious, but it would be worth it to get it right on the test. You know what I mean? Okay, so you guys test plus and minus 1, how about? You guys test plus and minus 1/2. You guys test plus and minus 1/3. If you're plugging that in, you'll do 1/3 first. Is everybody feeling good? Back there at 4, you guys a 6, and you guys a 12, and then I'll go through and test these bottom ones. I'll test multiple. I'll test all of these ones down here. Well, I tested all these bottom ones and also got none. So there were no rational roots. Now everybody graph it in your graphing calculator. Ready, set, go. Type that into your graphing calculator. Now I'm showing you making sense of this for you. So that's why I'm having you type it in. So everybody type in 12x to the 4th. Yeah, plus 14x cubed. It looks something like this, correct? Everybody? Okay, so it does cross. We do have 2 real roots, but they must be irrational because we tested all these and none of them came out. Does everybody understand? So we must have 2 irrational roots. Is everybody feeling good? Awesome, you guys are great. So do problem 135. Skip number 2 until we learn a little bit more. In fact, number 2 is a nightmare. We'll come back to it. So do problem 135 and 6 and skip number 2 until we learn a little bit more, and then it might help you. Okay, everybody continuing. Conjugate root theorem. We've already learned this, basically. Here we go, guys. So we know if, here we go, guys. So we know if we have imaginary roots, then its conjugate must also be a root. If we have an irrational root, its conjugate must also be a root. So everybody look right here. X is equal to 2 minus the square root of 5. If that's a root, then its conjugate 2 minus the square root of 5 must also be a solution, correct? Now remember, conjugate means change the sign in between only. So it should be plus, right? Everybody? Change the sign in between only. So right here, x is equal to 2 plus I, what's also a root? 2 minus I. So if this would have been a negative 2, this would be a negative 2 as well, correct? Just a change of sign in between. Okay, awesome. So right here, everybody look, it says write a polynomial in standard form with these given roots. So we have x is equal to 2, x is equal to 2i. Without it being said, what else is a root? Negative 2i. Nope, negative 2, no, right? I'm glad you said that actually, because if 2 is a root, its conjugate isn't a root. Because it's only, that conjugate root theorem is only true for imaginary solutions and irrational, right? Okay, now we're going to work backwards. If this was a solution, what was the linear factor? X minus 2 equals 0, correct? If x is equal to 2i was a solution, then the linear factor was x minus 2i equals 0. And then add 2i, correct? So x plus 2i would be a root. So before they were split apart by the zero product property, they used to be multiplied together. Now take my advice. Listen so that you can do it correctly and not go home and kill yourself because it's the worst. Okay? Here we go. So conjugates always need to be multiplied together first because think about it. Won't our middle term cancel out with conjugates? Yeah. No, like absolutely, right? No sure's, if, ands, or buts about it. So we'll have something much smaller if we multiply these two together first. We always multiply conjugates together first. X times x is x times negative 2i is negative 2, positive 2ix. I'm not going to multiply the middle term in because then what we get negative 2ix and the middle terms cancel out. So negative 2i times positive 2i is negative 4i squared. We know I squared is equal to negative 1, correct? So it'll be plus 4. So we have x squared plus 4, right? And then we have x minus 2. And now we can distribute. X times x squared is x cubed plus 4x minus 2x squared minus 8 in standard form, that's x cubed minus 2x squared plus 4x minus 8. Do we all feel good about that? So if we would have went backwards, anyways, let's do number 15 together. Here we go. So it says write a polynomial with these given roots. So we have x is equal to 3i, and we also have x is equal to what? Negative 3i. Imaginary roots and conjugates go hand in hand. Here we go. X is equal to the square root of 6, and x is equal to what? Negative square root of 6. So we're going backwards, right? So aren't we gonna, let's all think advancedly so we can skip some steps. We'll subtract 3i. Won't that be x minus 3i? We'll add 3i, so we have x plus 3i. We'll subtract the square root of 6, so we have x minus the square root of 6. We'll add the square root of 6, so we'll have x plus the square root of 6. And you guys know, right, if I do an example in class on the board, you don't have to show work without problem. So if you need to just watch, do that. Because I always see people writing, and then I'm like, are they like trying to do it, or are they like just not paying attention? If I do it in class, I know that. You don't need to show work. So everybody look up here. Take my advice and multiply the conjugates together first. So these are conjugates. So we have x squared. We can skip the middle term because it will cancel out. Then we have minus 9i squared. So we're going to have x squared plus 9. Everybody, are we good with that? Okay, over here, we have conjugates. The middle term is going to cancel out, so we just need to multiply the front term and end term. So we'll have an x squared, and then what we have minus the square root of 36, because 6 times 6 is 36. So won't that be x squared minus 6? Now we will double distribute combined like terms. X squared times x squared is x to the 4th. Then we're going to have minus 6x squared plus 9x squared minus 54, correct? Combining like terms, we have x to the 4th plus 3x squared minus 54 equals 0. Now guys, if I said solve this, wouldn't it be a u substitution? So do you see how we're going backwards? Questions? Okay. Do 7 through 18. Make sure you read the directions, because on 7 through 12, it doesn't say find the polynomial. It just says what are the other roots. Yeah. So you're doing 7 through 18. So, everybody listen, I have to tell you this pretty quickly, but it's actually really interesting. So now we're going to learn another theorem of roots of a polynomial, and it's Descartes' rule of signs. So Descartes' rule of signs is another way to help us find the real roots quicker a little bit. It's just going to tell us some information about the real roots. So Rene Descartes, actually back in the 1500s, that's like clear back in the day. So fun fact for you, all you ladies out there, it used to be super frowned upon for women to be good at math. Like they were supposed to be the homemakers and stuff. And so like if a woman was doing math and science, you were like frowned upon. So like Rene Descartes would have to hide in her bed at night with her sheets over her head, looking on it with a candle and doing math. And her parents would come and she's like, I'm not doing math, I promise. Like, isn't that kind of funny? Yeah, she like blows out the candle. I wasn't doing math, I was baking a cake under here. Yes. Very bad idea, yes. And that's how Rene Descartes died. Really? No. Okay, so anyways, everybody, okay, now we'll get back serious because we want to get through this. So what she noticed was, guys, Rene was looking at all these different polynomials, and she started to notice a pattern. So this is what she noticed, and then it was proven later, and now there's a theorem named after her. So what she noticed was, if you have a polynomial with real coefficients in standard form, the number of positive real roots is either equal to the number of sign changes between consecutive coefficients, or is less than that by an even number. So basically, guys, if you look at the coefficients in front of the variable, and you will count how many times the signs change from positive to negative and negative to positive. So let's say we're looking at a polynomial, and between this integer and this integer, it goes positive to negative. That's considered a sign change. And then a sign changed again. Then let's say sign changed twice. There was 2 sign changes in consecutive integers. Then that means there was 2 real roots or 0 real roots. It goes down in 2s. Does that make sense? 2 positive, I meant to say. So she looked at the original polynomial, and if it crossed 4 times, she looked at the sign changes, and if it changed 4 times, the signs between the signs in front of the coefficients, if it changed 4 times, then there were 4 positive real roots, 2 positive real roots, or 0 positive real roots. Then she tested the negatives, So she plugged in negative x into the function. She was looking at the negative x values of the function, and she noticed the same thing. If you look at it and you look at this number of times the sign changes between consecutive integers or consecutive coefficients, then, for example, if it changed once, there was one negative real root. Does everybody understand? It's not 1 or 0, it works in twos. So if it's 1, there is 1. Does that make sense, everybody? Okay, it'll make more sense once we practice. Now, that doesn't mean rational. This could be, like, it doesn't necessarily mean rational. It could be irrational or rational, meaning, so we could be looking at irrational roots as well. Does that make sense, everybody? Okay, here's my first example. If it didn't make sense, it will once you see it. So everybody pay attention so that it makes sense. So just right here, it says, what does Descartes' rule of signs tell you about the real roots? So we're going to just look at the original polynomial to see how many positive real roots we have. So we're testing the positive x values. So we look at the original polynomial. Where does it, how many times does it change signs between consecutive integers here? So from positive to negative, it happens, right? Negative to positive, it happened twice. So guys, it's either crossing 2 times or none. Does everybody understand that? In the positive x direction. So we have 2 positive real roots or no positive real roots. Does everybody understand? Now we're going to test the negative. So we're going to test negative x. So we're going to plug in negative x into our original function, kind of like when we were testing even, odd, or neither. So we're plugging in negative x. So we have negative x cubed minus negative x squared and then plus 1. So let's simplify this correctly on the test. Some of you did not simplify it correctly. Negative 1 cubed is negative 1. So negative x cubed. Careful here. Ignore this negative sign. Isn't negative 1 squared positive 1? So we're going to have minus x squared, correct? Then plus 1. How many times did it change signs? Negative to negative, that's not a change. Negative to positive, it changed once. So guys, we do have 1 negative real root. We know for a fact we have 1 negative real root. Now that helps us because in testing, when we were testing with the rational roots, I would be, since I know there's 1 negative real root, I'm going to test all my negatives first. But it could be an irrational root, so it might not be one of our possibilities, but that just helps me narrow it down. I'm going to test all my negatives first. Does that make sense, everybody? Yeah? Okay. And it might not be any of the negatives. So then we would know that there are no negative rational roots. Okay, so here we go. So now just look up here, same polynomial. Do you see how I graphed it? We said there were 2 or 0 positive real roots. It was 0, right? And we have 1 negative real root. Okay, sweet. Okay, let's do number 19. So it says, what does Descartes' rule of signs say about the number of possible real roots, positive real roots, and the possible number of positive and negative real roots? So we look at the original polynomial for positive real roots. Let's see how many we have possible. So positive real. So positive to positive, positive to negative. There's 1, negative to negative. So we know for a fact, guys, this has 1 positive real. So we have 1 positive real root. Does everybody understand? Let's see negative. So let's plug in negative x. I'm going to show my work just so we're not confused. So we have negative x cubed plus negative x squared minus negative 8 times negative x minus 12. Once again, I just be looking up here. So careful here. Negative cubed is negative. So negative 3x cubed. This isn't going to come positive, right? So plus x squared plus 8x, correct? Minus 12. How many times does our sign change? So 1 and 2. So this is either going to have 2 or no negative, that's an E, negative real roots. Does everybody understand how to use Descartes' rule of signs? Okay. Then I'm going to have you do one problem and then we've got to move on. So do number 20. And I'm going to give you a second to try number 20 and check with me and then we'll finish up. So for number 20, you should have said either 2 or 0 positive real roots, right? And then we know for a fact there are no negative real roots. Okay, awesome. Here we go. Number 23, it says, find all the rational roots. So now we're going to kind of put that together. We're going to use Descartes' rule of signs just to help us guess a little bit quicker. And then we're going to also use the rational root theorem. So find all the rational roots. So this one, we would do P over Q. The nice thing is, look, Q is 1. That's what we like. So all possible P over Qs. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, correct? Everybody? And then all divided by 1, so those are the only possible rational roots. Okay, awesome. Let's use Descartes' rule of signs now to talk about positive real. How many are possible here? So it changes once. So we know for a fact we have 1 positive real root. So I'm going to test my positives first. Now it might be irrational because it changes twice. Oh, good catch. So -5 to +2. It changes twice. So we have 2 or no positive. So I'm going to go on to negative. So if we plug in negative, guys, we're going to get, let's think advancedly so I can just show you quickly. That'll be a negative x cubed, correct? That negative is going to become positive in an x squared. So it'll still be -5x squared, correct? And then we are going to have negative x minus 2x plus 8. So let's see, how many times does it change? Once. So we have one guaranteed negative root, but not necessarily rational. So let's test our negatives though, because if there is a rational negative, we want it. So everybody, let's test -1 first. If you test -1 on 23, guess what we get? 0. So we know -1 is a solution. So I'm going to do a synthetic division to finish it off because I don't want to keep testing. So I have a 1, a -5, a 2, and an 8. Drop down 1, that's -1. Add straight down, -6. Up here is 6. Add straight down is 8. That's -8. Add straight down is 0. Remainder 0, it better be, right? So this is remainder constant x squared. So we have x squared minus 6x plus 8. If it factors more, you have 2 more rational roots. If it doesn't, we're done, right? So it does. So it's -2 and -4. So this is going to factor to be x minus 2 and x minus 4. So what are our other 2 rational roots? 2 and 4. So very good. So x is equal to -1. I'm going to write it up here. X is equal to 2 and x is equal to 4. Questions? Do you want me to do one more with you, or do you feel ready for me? One more. Okay, let's do this one. So let's do P over Q. Guys, if I'm going to do it with you, then that's fine, but you got to be with me. So P over Q, plus or minus 1, plus or minus 2, plus or minus 3. Because isn't this Q, this is P? Good. And then plus and minus 4, plus and, oh, yikes, plus and minus 12. This one's not a fun one. But we'll be okay. Q is 2. So plus or minus 1, plus or minus 2. So we've got to list these out. P over Q, possible. So then 3 plus or minus 3 halves, correct? Plus or minus 4 halves, which is 2, plus or minus 4. Plus or minus 6. 6 halves is 3. 12 is 6, right? Did I miss one? 12. There we go. Okay, haven't I listed them all out now? Okay, perfect. So what I'm going to do is now, before I do this, I'm going to use Descartes' rule of signs. Okay, we have only one sign change, correct? So we have 1 positive real root. So I'm going to test the positive whole numbers first. I'm going to just test, I like testing my whole numbers first. because I would like to use one of those for synthetic division. So if we test these, and this is 25, we're going to finally get to, we're going to test -3 and get 1. Does everybody understand? So we get -3. Okay, sweet. So we tested negative. Oh, that was not positive, though, right? Shoot. So without knowing. So we would have gone through and tested. Can I just tell you, because we only have a couple minutes left? +1/2 is one of them. Okay, so +1/2. So then I'll do a synthetic division, and I don't love doing it with fractions, but we can do it. So 2, 13, 17, -12. We would go through synthetic division here. So we drop down 2. 2 times 1/2 is 1. Add straight down is 14 times 1/2 is 7. Add straight down. 24 times 1/2 is 12. Add straight down 0. So this one's not too bad. Look, remainder constant xx squared. So we have 2x squared plus 14x plus 24 equals 0. Then I would factor out, I mean, you can do this 25 different ways. I personally factor out a 2 because then it's quick factoring. So I'm going to factor out a 2. Left is x squared plus 7x plus 12. Then we can ignore 2 for a minute because there's no variable. So what multiplies to be 12? 3 and 4. So this factor should be 2, x plus 3, x plus 4, correct? So set them equal to 0. 2, it doesn't matter. We don't ignore it because it's not a variable. So we get x is equal to -3, x is equal to -4. And then we also had a half. So there were 3 real rational solutions, correct? Okay. Okay. Just remember what problem this was for, because I don't have that up. Okay, so this is what I'm going to require, not all of the problems, because these take so long. I'm not going to do that one. You're going to finish the worksheet. Right now, I want you to cross out 35 through 40 just because that's too much practice. And then also cross out 47 through 49. Because these are tedious. I can't say they're not. They are. But you can do it. So that's 16 how you should be getting it set up. It's a pretty advanced one. Take my advice and make sure you multiply the conjugates together and the conjugates together. This is going to be on the video if you need to go back and watch it.
Yeah, I was doing it before.
Thank you. See ya.